So today I thought, let's skip the algebra for a bit, let's have a little bit of fun. I found this puzzle quite a few years ago. It was sent to me by a friend who wanted to help her daughter out with her maths homework. And on the face of it, it's a nice puzzle that you could probably solve in about 5 or 10 minutes, but there's a lot of room to go further with it. There's a lot that you can do, and actually it applies to one of the most important topics, I think, that we could be looking at today. You can take this as far as you want, and the chances are I will get carried away and take it a little bit further than I should, but that's half the fun in mathematics. Otherwise, let's get on with it. So, the puzzle that I've got for you today, as I like to call it, is £31 exactly. We have been given 5 bags that we're going to put money in. We have also been given exactly £31 coins. Now, I don't know about you, but that sounds like a perfect start to my day, being given 31 quid right off the bat. But what do we want to do with them? We want to put these 31 coins into these bags in such a way that if we go into a shop, we can, by handing over any combination of the bags, give over any amount of money between £1 and £31. So we've split the money, the 31 quid, into these 5 bags. If I go into a shop and the shopkeeper says I want 17 quid, we could hand over one of the 3 bags. If he said, well, in fact, actually, I want 11 quid, we could hand over 2 of the bags that add up to give 11 quid. Can you put the money into these 5 bags in such a way that you can give the shopkeeper any amount of money between £1 and £31? Can you do it? So, what I love about this problem is that there are loads of different ways of solving it. Some people have come at it by trial and error. Some people have had a bit of a system in place. Some people have spotted the answer right off the bat. I absolutely adore this puzzle for that exact reason. In fact, I did try to solve it randomly. I picked a couple of numbers, say for instance, 17 and 11. I tried putting 17 and 11 together to see if we could make it work. 17, sensible set of numbers to start off with would be 10, 5 and 2. That gives me £17 right there. So 3 of my bags are 17, 10, 5 and 2. And what do I need to add to that? Well, I've got my 10 from before, and then I've got 1. So there's my 4 options, 10, 5, 2 and 1. With that, I can make 3 quite clearly. We can make 6. We can make 10 plus 5 plus 1 to get 16. We seem to have quite a range of numbers. But then what if I wanted to make something fairly simple, like, say, 7? Oh, wait, we can do 5 plus 2. Perfect. This is working. We can even make 8. We can't make 9. We can't make 9. We can't make 4. We certainly can't make 20. Oh, well, it's okay. We've got 5 bags, so what if I just chuck in another 10? Well, now we can make 20. But we can't make 4. Alright, so let's scrap that. What if we just had another 1, for instance? Let's combine these. We've got 5, we've got 17. We can make 18, 19. We can make 19. We still can't make 20. Because remember, I've only got 1, 2, 5, 10. Oh, well, we could make another 10. But you can see already, let's say I were to list these out. I've got 1, I've got 1. I've got 2, 5, and 10. So because of the second 1 that I had to throw in to give us a 4, I now can't make 20. In fact, the maximum I can get from this is 10 plus 5 is 15, 16, 17, 18, 19. The maximum amount I could make is 19. And we can't even be convinced that we can make all of the numbers from that. So what if we were to try it a different way? What if we were to say, from 17, I want to use just my 11 plus 6. So we start small, because now what we know is that we can make 11, and we can definitely make 6. So any other numbers from that, maybe we'll just break it down. We'll see what we can fathom from it. You'll find if you try it this way, there'll always be a set of numbers that you can't make, or there'll be some that just get out of the way. So let's try looking at it a different way. First thing we need to do, I think, is give these bags a name. Now, the first bag, I'm going to call bag, you guessed it, 0. Don't you start counting from 0? You'll see why I've done that in a bit. Mathematicians, certainly, and some very good friends of theirs, love to start counting from 0. And for anyone who gets that hint, I think you've figured out the answer to this already. So we're going to call the first one bag 0, bag 1, bag 2, bag 3, and bag 4. So I've labelled them quite carefully. This will make sense to you in a little bit. Just trust me, for now it's more of a name. The reason that I'm calling this first one bag 0 rather than bag 1 is because if I didn't have any money in one of the bags, well, frankly, we've wasted it. So we might as well start with £1, just the 1, being in that bag. It would seem to make sense. It's the only way to make £1, so we need to have a bag with 1 in it. But it stands to reason at this point that I can't make 2 from just that bag alone. So we'll call this one bag, we'll call bag 1 2. You might be thinking, well, we can't make 3, so clearly we have to have 3 in there, but this is going to run out fairly quickly. Well, actually, if we were to combine bag 1 and bag 2, we know that 3 is equal to 2 plus 1. Okay, fine, fair enough, we can't make 4. I get that. Some of you might be starting to spot the pattern here. We can't make 4, so we put 4 into bag 2. Can we make 5? Yes, 5 is equal to 4 plus 1. Can we make 6? Absolutely, that's equal to 4 plus 2. Can we make 7? Yes, that's 4, 2, and 1. We can't make 8, and I think you can see the pattern here. Now we can make 9 by 8 and 1. We can make 10. We can make 11 and 12. In fact, 8 plus 4 plus 2 plus 1, that will give us 8 plus 4 is 12, 13, 14, 15. We can make anything up to 15. So on the assumption that we can't make 16, we'll put that into bag 4. I claim that every single number can now be made using any combination of those bags. If you don't believe me, I'll give you a hint, but by all means, please pause the video and try this for yourself. You don't have to create all the numbers from 1 to 31. You can if you want to argue that I'm correct on this one. It's entirely up to you. But just to prove my point, let's go with, say, 17. That's actually a fairly easy one, because we've got 16 to begin with, and all we need to add to that is 1. We've also got 11. Okay, so we don't need bag 4, that's far too much. But if we started with bag 3, that's 8. We need another 3 to get from 8 to 11. Well, that is 2 plus 1. If I were to pick a number off the top of my head, today's date is, let's go with 29. Today's the 29th. Well, we're clearly going to need the 16. And if I were to take away 16 from 29, then we would be left with, that would be 13. So I'm definitely going to need the 8. 8 off of 13 is 5, but that is 4 plus 1. Let me just double check my maths to make sure I've got that right. 16 plus 8, that's going to give us 24. 24 plus 4 is 28. Plus another one is 29. Have a go at it for yourself. What's your birthday? See if you can make your birthday using this system that we've got here. If, however, you want to know the maths behind why this works, by the way, that's the puzzle solved. That is the combination. That is the full set of answers. But what you have inadvertently done, and one of the reasons I really love this puzzle, you have inadvertently just learned about binary. You've learned about binary mathematics from a puzzle that seemed to have nothing to do. What is binary? That is the basic language that your computer is using right now. It's the basic language that your computer is using to turn all the bits of information that came through over the internet into the video. It's what the computer used to record me making this video and everything that happened in between. When you're going to the bank, when you're playing on the PlayStation, when you're on the phone to your friends, your computer is using this very, very simple, beautiful, elegant system that helps it to make sense. Your computer only understands, at its basic level, 2 things. 1 and 0. That's it. That's all your computer knows at its fundamental level. 1s and 0s. But you're looking at this thinking, but David, these aren't 1s and 0s. This is a 1, a 2, a 4, an 8, and a 16. If you know anything about the laws of indices, you can try this on your calculator, you know that 1 is 2 to the power of 0. Anything to the power of 0 is 1. 2 Well, that's 2 to the power of 1. One lot of 2. 4, most of us know, I think, is 2 squared, 2 times 2. 8 is 2 cubed. And 16, 2 to the power of 4. And again, that's all well and good. What you are looking at actually are all the numbers in base 2. So what becomes really nice about this, yeah, we've only gone as far as 31. What if we wanted to push it higher? I claim if we were to double this and subtract 1, so 32, let's say we wanted to go as far as 63, sorry, double it and add 1. If we were to add another bag over here, so we'll call it bag 5, I appreciate it does look more like a little pumpkin, but trust me, if we were to make bag 5 and we were to call this 32, then we could add all of these up and we get any number up to 63, which I think is great. So, adding one bag, we effectively double the amount of numbers that we can create. But I digress. By the way, 32, you might want to recall, is going to be 2 to the power of 5. So you can see the trend as we increase, which I think is great. Now, to bring it back to the binary, as far as we're concerned, what your computer understands is a combination of zeros and ones, and it will put those into slots. It will make any combination of those that you like. So we can have zeros and ones. Anyone who's watched The Matrix or anything like that, you'll have seen these zeros and ones flash up on the computer, and this really is what your computer's doing. So as far as the computer's concerned, let's pick the number that we went with before. Let's go with 11. 11 was quite interesting. And assume that we have these 5 bits. So a bit is an individual piece of information. It's a 0 or a 1. So as far as your computer's concerned, the number 11, there's no 16s. There is 1 8. What did I have to add to that? There was no 4s, sorry. There is 1 2 and 1 1. So in 5 bits, 11 is equal to 0, 1, 0, 1, and 1. We have gone a long way from that puzzle where we were just looking at money, and we've already broken the back of binary mathematics. We can do loads of really cool stuff with that, actually. We can find a very, very elegant way of finding pretty much any other number using what is known as binary mathematics. Let's have a look at my other number, 17. Let's say I want a really quick way, rather than trying to prat on with this and find some other number. Is there a nice, elegant way of finding out exactly what could give me, say, 28? So let's bear in mind that 17 was 1, 0, 0, 0, and 1. Why can I say that? Because that there, the one on the left represents 16, and the one on the right represents 1. Now I want to make, say, the number 28. Now, you know from home that if you were to do 11 plus 17, you'd get your 28. Now let's look at what happens if I add these numbers together. So I'm just going to try and bring up my mouse so you can see what I'm going for. 11 plus 17, how do we add in binary? That 1 plus 1, now that should give you 2, but you'll notice we don't allow 2 in binary mathematics. So what can I do? Well, I can treat it like anything else. We can carry over the 1. We can carry it up just like we do with tens. If we go higher than that, then we just carry it over. So we've got 1 plus 0, and that should be 2, so again we need to carry a 1 over. Now I've got 1 plus 0 plus 0. Ah, that's 1. 1 plus 0, that's 1. And 0 plus 1, that's 1. Did that even work? I'm going to change my pen to blue and we'll just find out. So let's think about this in binary. Do I have a 16? Yes, I do. Do I have an 8? Yes, I do. And do I have a bag 2, which is a 4? Yes, I do. What is 16 plus 8 plus 4? Oh my god, it's 28. That's binary addition that we've covered. Now, you'll see what I mean when I say I got completely carried away by this puzzle. I genuinely think it's beautiful. We started off talking about putting some money into bags. And from this, we've effectively uncovered the introduction to binary mathematics. The reason that our computers work. What else have we done with it? We've gone from 31, and we've said, right, we can do that with 5 bags. What can we get up to with, say, 6 bags? We can actually double that. We can get as far as 63. And that's how your computer works. It's an exponential growth. You only have to add in one extra place, and you can double the amount of stuff that you can play with. And that is the beauty of modern day computing and mathematics. Or it's the beauty at a very elementary case, at the very least. I've had my coffee, I've calmed down, took you on a very, very nerdy rant there. I'm not going to lie to you, I'm not sorry. I really enjoyed that. I love how beautiful and elegant all of this stuff is. And that's just the basic level of it. That's just the basics of what we can do with random little puzzles that turn out to be worth far more than they are. I genuinely think that the essence of mathematics is a nerd solving a puzzle at home that somebody else happens to find useful somewhere else. I do also think that there is a joy in mathematics in terms of solving a real-world puzzle, figuring it out, extracting all of the random stuff that sits next to it, and then turning it into something that's wonderfully mathematical, looks very pretty, and solves a puzzle somewhere else. But maths always tends to solve more than it ever expected to. With that in mind, I'm going to leave you to it for today. I've had a wonderful time showing off this little puzzle. I hope you've enjoyed trying to solve it at home. As always, if you think that this was worth 20 pence of your time or anything, there is a PayPal account below. Thanks so much to the UTC for giving me time to make these puzzles and get them out. It really is a wonderful part of the job. And thank you to you for watching at home. I will see you next time. Take care.